Hi, Pre-Cal. Let's talk 10.6, counting principles, permutations, and combinations. First thing in 10.6 is the fundamental counting principle. And here's a quick example to help you understand the fundamental counting principle. Suppose that we are going to have lunch at the Pizza Time Palace, and they have a lunch special. Here are the options for what's available. You can get one of two sizes, a small or a large. You can get one of three crusts, a thin crust, original crust, or a thick crust. And then for the lunch special, you get to pick one topping. 1, 2, 3, 4, 5, 6, 7. 7 toppings to choose from. So the question is, at the Pizza Time Palace, how many lunch special pizzas are there to choose from? So let's think about this. In order to utilize the fundamental counting principle, it's all about choices. We're simply counting choices here. So what do we have? Oh, and of course, is order important? No. It's the same pizza whether you start by choosing a topping first, then a crust, and then a size, or maybe the crust and then a topping and then a size. It doesn't matter. The fundamental counting principle just counts choices. So, how many lunch special pizzas are there to choose from? Well, first of all, let's choose a size. How many sizes are there to choose from? There are 2. And then, how many crusts are there to choose from? Well, there's 3. And then, how many toppings are there to choose from? There are 7. So 2 times 3 times 7. 6 times 7, 42. There are 42 possible pizzas that you can get for the lunch special. The fundamental counting principle, basically, you just multiply the choices together and that's how it works. It's quite simple. Next, permutations. Permutations is a synonym for arrangements. And if we have an arrangement, clearly an order is implied, and it's important. So anytime an order or a ranking is implied, you have a permutation. So here's an example. You and your friends are all eligible, equally eligible, to be class officers. A president, a vice president, a secretary, and a treasurer will be chosen. If the officers are to be selected from the 20 friends, how many possibilities are there? So this is implying that everyone is equally eligible to be president or vice president or secretary or treasurer. But a ranking is also implied because the president is clearly more impressive of office than the vice president, secretary, and treasurer. So we're looking for possibilities of ranking 20 friends 4 at a time. So we can do this 2 ways, which I'll fit right on the bottom of the paper here. So we're going to be choosing independently. So if we look at the first blank represents the president, the second is the VP, the second is the secretary, and the fourth is the treasurer. So if everyone is eligible to be president, how many choices are there for president? Well, there's 20 friends. So there are 20 choices for president. Now, a person cannot be president and vice president, so these 2 events, choosing a president and choosing a vice president, are mutually exclusive of one another. Therefore, there are now 19 choices for the VP, and then 18 for the secretary, and then 17 for the treasurer. If we multiply all these choices together, 20 times 19 times 18 times 17, we get 116,280 possible arrangements from 20 friends being arranged 4 at a time. Now, there's another way to do this, and it's a formula. It is the NPR formula, which is n factorial over n minus r factorial. So obviously we're going to use our calculator here because it's factorials and they're very, very large numbers. So this would be 20 friends being permutated, arranged 4 at a time. So if I go to my calculator, 20, and then this is, whoop, wrong thing. Sorry. So try again. 20 alpha F2 number 7 20p4. Check it out. I get exactly the same numbers as if I would have just said 20 times 19 times 18 times 17. Sometimes it's easier just to do this rather than use the formula. 1 1 6 2 8 0. As you can see here, distinct arrangements, when you have mutually exclusive events, they get quite large quite fast. So here's a fun problem to consider. Let's arrange the letters in the word precalculus. We want to know how many permutations, how many distinct permutations. So they all have to be different. So think about it. Is a permutation going to be distinct if I just switch the 2 C's? No. Or I switch the 2 L's or the 2 U's. You see where this is going. This particular word has repetitive elements. So we have some mutually inclusive situations here. But here's how it's done. First thing we got to do is how many elements are actually in the word precalculus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 elements in the word precalculus, elements, letters in this situation. There's 11, but because some are repetitive, we are going to divide away some of our non-distinct arrangements. So let's count the repetitive elements. So we have 2 C's, so we'll be dividing by 2 factorial. We also have 2 L's, L, so another 2 factorial. Now, of course, 2 factorial is just 2, but truly, when you're looking at the repetitive elements, you put them in terms of a factorial on the bottom, and then the U's, 1, 2, 1, 2, and 2 factorial. So that's everything. So when we work this out, and just to be very thorough, let's look at this on the calculator. So you can find factorial on the alpha F2 menu, or you can also find it on the math menu. So 11, actually I'm going to go to the fraction first since this is a fraction. 11, and the factorial is a little harder to get to if you use math. It's on the probability screen. It's choice 4. That's why I find the alpha a little bit more conducive. So 2 alpha F2, 9. And let's not see this out of focus. There we go. It's a little better. Okay, 2 alpha F2, 9. Obviously, since this is 2 factorial, which is equal to 2, I'm just going to say 2 for this last one. But the fraction is helping us follow order of operations here. If you don't use the fraction bar, then you need that entire denominator to be in parentheses. But what you can see here is even though we're dividing this by 8, this is quite a substantial number. 4, 9, 8, 9, 6, 0, 0. So in the word pre-calculus, there are 4,989,600 distinct arrangements of the letters that make up the word pre-calculus. So permutations, quite large, quite quickly. Let's go to combinations. Combinations. order not important, which of course, if we were in class, would lead to the conversation of, out on your locker, do you have a combination lock or a permutation lock? I believe it should be named a permutation lock because the order that you dial your combination, permutation, it actually is important. But here's a good example of one combination that could be put into 6 distinct permutations. Burger, fries, Coke, burger, Coke, fries, Coke, burger, Coke, burger, fries. So, one combination, but 6 distinct arrangements. If we were in class, I would say it doesn't matter how you sit in the desk, you're still Mrs. Hendry's one class. The class is a combination because order is not important. So, to find the number of distinct combinations, we use N-choose-R or NCR. So, let's go back to the example we had earlier, the 20 friends. The 20 friends, but now instead of trying to rank a president, vice president, secretary, and treasurer, we simply want a committee of 4 to plan an event. So a ranking is not implied. So is ranking implied? No. Is an order important? No. We simply want a committee of 4. So if we just want a committee where everyone has equal power, this is simply going to be 20 choose 4. Now, the NCR formula, and it is touched on in the binomial theorem chapter or section, it is n factorial over n minus r factorial times r factorial. So in this case, the number of combinations is limited in this situation because we have an extra factor in the denominator. So if we plug this in, we get 20 factorial. 20 minus 4 is 16 factorial times 4 factorial. We can actually work this one out a bit. 20 times 19 times 18 times 17 times 16 factorial over 16 factorial, and then 4 times 3 times 2 times 1. So let's do a little magic here. The 16 factorials cancel, obviously. And then, let's see, 4 goes into 20 5 times, and 3 times 2 is 6, and 6 goes into 18 3 times. So essentially, we're left with 5 times 19 times 3 times 17. 5 times 19 times 3 times 17. We get 4,845 different ways that we can make up a committee. Now, obviously, we could always just do this with the NCR on our calculator. So here we go. 20 possible committee members chosen 4 at a time. We can use the alpha F2 to get to option 8, which is NCR. So 20 choose 4, 4,845. So, ladies and gentlemen, that is section 10.6 in a nutshell. We'll talk more about it in class. Have a great day.